Hello, welcome everyone to our session about Azure AI Search. So I am Pamela Fox. I'm from the Python Cloud Advocacy team at Microsoft, and I've been running a lot of these sessions because I love working on these AI RAG chat applications, especially in Python. And then Sri, can you introduce yourself?
Hey everyone, I'm Sri. I'm from the Azure AI Search team. I've been with Microsoft for 5 years, and this is my first opportunity to join a hackathon and then present the knowledge I have about the search, and then we'll go from there.
Awesome. Yeah, so I've been working with Sri over the last 6 months or so on the Azure AI search demo that we've been using for this hackathon. And Sri has made a lot of the improvements to that repo, especially in terms of how it works with Azure AI search. So he's an expert in that. So we'll both be talking today about our Azure AI search best practices, so you can understand it at a deeper level and figure out how to really optimize it for your AI chat application. So this is where we are in terms of our session, right? So we're running this AI chat app hack from January 29th to February 12th. Everybody is welcome to join. It's all about how we can make these RAG chat applications in order to chat on custom data for whatever domain you're interested in, right? So we're on day 3, and we've already had actually 3 sessions before then. They're all recorded on YouTube, so you can go back, watch any sessions you missed, and then please do join us for this session and all the sessions going forward, because we're going to be talking about a lot of topics that are really helpful when you're developing these sorts of applications. Today, we're focused on Azure AI Search, which is what we use for the RAG chat solution that we've been hacking on, because it's really an incredible solution for search. And we're going to be talking about how to really understand how to use it well for our RAG applications. So let's just revisit RAG. RAG stands for Retrieval Augmented Generation. That R stands for retrieval, which is when we retrieve the sources, right? So the user asks the question, and then we take that question and use that to search some sort of knowledge base. That's when we do the retrieval. And then we get back the results, and then we can send both the user question and the results to the large language model and say, hey, answer this question based only on these sources. And then the large language model can respond accurately and synthesize the information really well and convey it to the user. So the thing is, like, a lot of times when people are developing these applications, they'll say like, oh, I don't think the answer is good enough. Like, how do I change my prompt to the LLM? But a lot of times, if the answer isn't good enough, a lot of times it's because the retrieval isn't good enough. In my experience, is if you get the retrieval working really well, then you'll generally get a good answer, a high quality answer. So we really want to talk about retrieval and how to optimize retrieval, because it's so important for having a really well-grounded, high quality answer. And so here, this is actually this graph from a paper, Lost in the Middle, which talks about where they did experiments with sending lots of information to an LLM to see how well it was able to, answer questions and how accurate the answers were. And what they found was that if they sent lots of information to an LLM, then the LLM would get kind of lost and would miss out on some information that was in there. So what they realized is that you really want to send just the right amount of information to a LLM, not too little, not too much, right? You want to send the right amount of information to LLM and not overwhelm it with information that's not relevant. So that's why it's particularly important to have really good retrieval, because what we want to do is to say, okay, we're going to search the knowledge base. We're going to get the top 3 results, 3, 5, not too many, right? Like probably not more than 10, right? So we're going to get those top just few results and then send only those results to the LLM, so that we're giving it, the best information for it to work on and not giving it information that isn't useful. So that's why it's particularly important that we have, when we do a search for information in our knowledge base, that those first 3 to 5 results have the information we're looking for, so that we don't send too much to the LLM. So when it comes to Azure AI Search, when we want to do retrieval, the best approach is to use a hybrid approach, which means do both a vector search and a text search. And then on top of that, using something called the semantic ranker model, which is another machine learning model that re-ranks the results that comes from into the fusion of these two. So that is the optimal way to search Azure AI Search. That is what we default to in the RAG chat repository that we've been hacking on. So, you'll see this in the UI. Let me go and show that here, right? So this is the repo we've been working on and forking and hacking, and you can see in the UI the retrieval mode defaults to vectors and text, which is hybrid, and then also defaults using semantic ranker for retrieval. So we default to these because we know from experience and from research that this is the optimal retrieval. So what I want to do now is actually do a deep dive into vectors and vector search, because I think vectors are new to a lot of people. They're fairly new for me. And I think it helps to really understand what vectors are really good at, and then also what they're not necessarily as good at. So let's talk about vector embeddings. So a vector embedding takes some sort of input. So in this case, like the word dog, right? We take that input and then we send it through an embedding model, which is a machine learning model. We send it through an embedding model, and then we get back a list of floating point numbers. So different models, there's lots of different embedding models, and these different models, they can output, embeddings would have different lengths and, which represent different things. So you need to pick a model that works well for your input and for your use case, right? So a classic model that we've had for a long time is the word to vec model, but that only encodes a word at a time. And that would output a vector length of 300. One that we use most of the time, especially in our, in all our samples, is the OpenAI ADA002 embedding model. And this one can process text up to 8,191 tokens. So it can actually process large amounts of text. It can take a whole big lot of text and then compute an embedding for it. And those vectors always have a length of 1,536. So this is with ADA002. Now, OpenAI did just announce that they have new embedding models, and they only announced it like 4 days ago. So I have not had a chance to even dig into it. But just an FYI that's on the horizon, that we're going to have more embedding models to pick from. And so the thing to consider is, what can it encode? Is it text? Is it long text? How long of a text? And what sort of vector dimensions are you looking at? And then there's also in the Azure computer vision model that can do images or text. And it's really, really cool. And Matt's going to be talking about that tomorrow in the vision talk. So let's go ahead and actually compute a vector. So here we go here I've got a notebook set up, and the first thing I do in this notebook is I connect to Azure OpenAI so that I can use the ADA002 model here. And then I just have some convenience functions that pass in some, text to that model and get back the list of floating point numbers. Okay, so we set that up. All right, so we're all connected. And then let's try just a single word, right? So we can say get the embedding for dog. And it actually takes a few seconds. The first time it's just making that connection. Okay, and we can take a look at that vector. It's very long. We can confirm that it has a length of 1536 because that's the length of all vectors for this model. But we can do more than just single words, right? We can do whole sentences like a dog just walked past my house and yipped like a Martian. Yip, yip, yip. Okay. So we can go and get the embedding for that. So this model can come up with vectors for anything up to 892. Now, we usually recommend, when we're doing RAG apps, we usually recommend not going more than 512 tokens or maybe 1024, but it can calculate embeddings for up to 8,192. All right, so we get that back. But then what do we do with this? Why did we just make a list of floating point numbers? What's the point? Well, the reason we come up with these embeddings is because then we can do similarity between things based off their embeddings. So if we can find a way to take some input and turn it into a vector embedding, then we can compute similarity between vectors. And then there's so much we can do with similarity. We can do search, we can do recommendations, we can do detection. There's so much we can do once we can do similarity between things. So for these embeddings, we need to calculate some distance between them. And the usual distance measurement to use is cosine similarity. There's other ones you can use as well, but especially for the ADA model, we use cosine similarity. And that's just the dot product of the vectors over product of the magnitudes. And, you know, the way you can think of it is that if the two vectors are very, very close to each other, then the angle between them is very close to 0, and the cosine of the angle would be very close to 1. And then the farther away the vectors get from each other, then the angle is getting bigger and bigger, and the cosine is getting, down to 0, or even it could go down to -1. That's, the most negative that a cosine value could be. And so that way you can decide, based on the cosine, whether how close things are to each other compared to other things. So let's go ahead and actually try to compare some vectors. So here we've got some sentences. So let's say, let me do these ones. Okay. So we've got these 3 sentences, they're all the same. And then these 3 sentences here. And what I'm going to do is compute the embeddings for all of these, and then compute their cosine similarity. And here I'm using NumPy to do it. And then, see how these cosine similarities compare. So what we can see is that when we compare the new movie is awesome and we compute its cosine similarity, it has a score of 1. And that makes sense because it is exactly the same vector, right? So it should be 1. Now, when we say this one compared to this recent movie is so good, it has a score of 0.91. So, that's not as similar as 1, but it seems to be somewhat similar. Now, if we compare it to the dog went to the park, that has a score of 0.77. And so when you look at these, you might think like, well, maybe the dog went to the park is actually similar to this. But in fact, this isn't actually very similar, at least for this model. So I can then replace this with absolute nonsense here, right? And recalculate. And that still has like around in the 0.7s, right? So what I found is with the OpenAI ADA002 model, the cosine similarities tend to range between 0.7 and 1. You never see them get down really low to 0 or -1. It just doesn't happen. So you can imagine that this is all like in this vector space, right? This multi-dimensional vector space, which is really hard to imagine because we can't really imagine more than, 3 dimensions. But just imagine even in 3 dimensions, you can imagine that all these vectors are in fact inside like a cone. Like I think of it as like the ice cream cone of the vectors. They're all inside this cone. And so the ones that are closest together are the most similar, but even the ones that are the least similar are still inside this cone. So they still get these fairly high cosine similarities. So what's really important is to look at the relative differences between the cosines and not look at their absolute differences. I've also got this other demonstration here where I looked at, I calculated the embeddings for 1,000 words, and I did it across a few different models. And so for OpenAI, you can see that for dog, the most similar word in this 1,000 word set is God with 0.86. And then the least similar is Catalonia, or actually isn't, with 0.74. So this really shows that the similarity tends to range between the 0.7s and here it doesn't even get higher than 0.86. I also did the same thing with movie title embeddings. So these are all Disney movies. So I just calculated embeddings for a bunch of them. So you can see like Many Adventures of Winnie the Pooh has a 0.93 similarity with Winnie the Pooh. That's very similar. That makes sense. And then least similar, we go down to like, Metro has 0.72. So that's just to try and give you some intuition about cosine similarity, especially if you're using it with the ADA model. It is going to depend on the model. Like for Word2Vec, you actually see a much bigger range of the similarity. But I thought that was interesting to understand cosine similarity a little bit more. All right, so once we have similarity, then we can use it to do vector search. And the way that you do it is you get what you're going to search for, you compute the vector for that thing you're searching for, and then you search all the other vectors and find the ones that are close to that based off of cosine similarity. So let's actually try that out. Okay, so what we're going to do is load in those movies, right? So I've got those embeddings already. So my vector, my little mini vector database is just going to be in memory, and it's going to be a bunch of movie vectors. And then I've got a query. So here, let's start with Winnie the Pooh, since we just, oh, well, now that's already in the query. Actually, we need to do one that's not a Disney movie. What's not a Disney movie? Well, Barbie is not a Disney movie. Okay, so let's query for Barbie. And we're going to turn that into a vector embedding. So we get back that list of floating point numbers. And then we calculate the similarity between that vector and all the existing vectors in that Disney movie database. And then we're going to look at their scores in a table. So let's see. All right. So what we can see is that the most similar one was Babes in Toyland. It makes sense because Barbie is, yeah, that makes sense. Barbie's a toy. And then the least similar is Winnie the Pooh. Or not the least similar, sorry, of that list. So actually, that's actually pretty similar because these are the top 10 closest ones. So Winnie the Pooh is actually fairly similar to Barbie, as it turns out. So let's try My Neighbor Totoro. And that's a Miyazaki movie. And you can see it gets back like Toy Story because, you know, it's about like a large creature. Zootopia seems to be similar. And it actually did find some Miyazaki movies as well because apparently Disney distributed them. So this is Spirited Away and then this is Ponyo. So I find it really interesting. This is just based on titles. So it's really interesting with these embedding models because they end up embedding things both, like they end up embedding so many different aspects of, you know, of the string, right? They embed things about like the spelling of it. They kind of embed things about their, you know, how they're connected culturally, because it's all just based on how they learned about the world. And this is, you know, this is how the OpenAI Ada model learned about the world. In their version of the world, these things are similar to this thing, right? And I think it's fascinating to see, and you can do so much with this. Okay, and so that's just to give you a little intro to vector search. Now we can use vector search in Azure AI Search. It is generally available now and is built in, enterprise ready, scales really well, and it's also integrated with lots of packages like Semantic Kernel, LangChain, Llama Index, the Azure AI Studio. So you can use it in lots of places. So let's try it just with the SDK. So here I'm going to use the Python SDK for Azure AI Search. So first I just, you know, import a lot of stuff from the SDK. I connect it to a search service that I've already set up. I connect with my credentials to OpenAI. And now I'm ready to actually, you know, set some stuff up. So I'll say, I'm going to make up an index name, teeny index. And then in that index, I'm going to have a simple field ID. And this is the primary key. So generally, when you're making a search index in Azure AI Search, you want to have a primary key, just like you'd have in a database row. And then we have this additional search field, which is the embedding field. This is the one that's going to store the vector. And so I need to say, I want to be able to search it. And then I tell it how many dimensions it is. In this case, we're going to do it, just start off with a small vector of just 3, a length of 3. And then I give it a profile name. And this profile name is necessary in order to tell it what indexing algorithm to use. So once we start to have vector search at scale, we need indexing algorithms that can efficiently index and query those vectors, right? Because when I did this example here, I literally compared every single, you know, existing vector to that new vector. That's fine when you only have 500 Disney movies to look at. But once you start having, you know, thousands and millions and all that stuff, you're going to need a more scalable approach to searching. So that's what you set up here. And in this case, I'm using HNSW, which is a very popular indexing approach for vectors. So then I create the index. Let me run that. Okay, so that's created. And now I'm just going to insert some documents. So these have really, really short vectors here. All right, so that is now in the index. And so now I can actually do a search. So let me search for something that looks fairly similar to what's in there already. And you can see it returned back, like, oh, it's saying like ID3 is actually really, really close. And it gives a score here. And actually, maybe Sri, you could remind me if this score, when you're doing just vector search, I think the score still isn't the exact cosine similarity. There's a document that talks about it. It's slightly modified, isn't it?
It's slightly modified. Yeah, it's not the exact cosine score. We have plans to reduce it, but right now we don't.
Okay. Yeah. So when you look at this, it's not necessarily the cosine similarity, and there is a document that talks about how to go backwards from it if you some reason really wanted it. But generally what matters is not the absolute score. Usually what matters is the relative scores and the ranking in the results, right? And are you getting the top results that you expect, right? So then we can go and change this to like -1, and that's, and then we can see that the scores are less, and we also got things back in a different order. So that's basically how how you can set up a index that has a vector search field, and then how you can search it. So let's try this with like an actual index, right? So here I've got my full index. And actually, let me go ahead and show you it in the portal so we can see this is the search service. So I'll go to the portal and find my search service so I can show you this index. All right, so here we go. And then we can go click to indexes. And I have so many of them now from this demo. But this is the big one that we're going to search. So you can see it has 691 documents and about 20 megabytes of documents. So it's actually not a super big index, but it's certainly bigger than that teeny one. So this is what the documents look like that are in here. Remember, these are actually chunks of our PDF documents. So we can see that each of them has an ID. It has the text content. It has the embedding, which is the vector version. And this embedding is always going to be 1536 dimensions because we're using the ADA002 model to calculate it. And then we have the page number that it came from and the file number it came from. So this is what our index looks like. And this is what we're going to search. So we go back over to our searching. So this is the index. We create a client to connect to it. And then our search query is going to be learning about underwater activities. So I calculate the embedding for that. And then I pass in that as a vector query. So I say vector equals this vector. It's going to get the 5 nearest neighbors, and it's going to search the embedding field. So you need to tell it which field to search, because you could potentially have multiple fields on your index that are vector fields. You're not limited to just one, right? So you might want to, make a vector for the title, make a vector for the body. Like there's lots of things you could do there. So we're going to search just the embedding field, and we're not going to pass the text in at all. So search text equals none means we're doing a vector only search. All right, so we run this code. And what we see is that the top result says some of the lessons include scuba diving, skiing and snowboarding, surfing. So this is the power of vector search, is that we search for underwater activities, and none of these terms are actually in this result. However, what it saw was that, hey, underwater is a similar concept. It's a similar vector to, not skiing, like surfing and scuba diving, right? So it was able to find underwater things, even though that term wasn't in the content at all. So that's what we're really getting out of vector search, is the ability to find these similar things, even when people aren't using the exact words to describe them. So that's really cool. And what you see in that demo, we used the HNSW search. So that is the a graph method which uses your, has very good performance for doing vector search at scale. And that's what we generally recommend. You can do an exhaustive search if you think it really makes sense for your use case, like if your index isn't that big, or you have like you're using filters that really get the search space down to a small size, then you might want to use exhaustive search. Most people are probably going to use HNSW for performance reasons. Here's some additional things that we can do with vector search. So we can, we can combine vector searches with other filters, right? Because you may want to be doing other things like, breaking down by a certain category, right? Or looking at timestamps and recency. You can decide whether you're going to run a filter before the vector search or after. Typically, you want to do it before so that there's you narrow down the space before you try to find the similar vectors in that space. But there may be situations where you want to do it post, so that's an option for you as well. Another thing you could do is you can have multiple vectors that you're searching for. So, here's the example where you might be searching both the body vector and the title vector. But another example that we'll see tomorrow is doing multimodal vector queries. So if you're trying to search both the text, maybe text embedding, image embedding. So there's lots of things that you can do with these vector queries. All right, so vector search, really cool. Hopefully you're excited about having vector search capabilities. And we also saw on Monday, we saw from like the Cosmos DB Mongo team about vector search support for Mongo. And so we are seeing lots and lots of vector databases and normal databases being able to handle vectors. So that's really, really good because there's so much that so many better results that we can get when we have vector search. However, what you really want to do is hybrid search. Hybrid search is going to get you the optimal results. And when I say hybrid search, what I mean is that we're doing vector search, we're doing keyword search, we're fusing those results together, and then getting the best results from that mix. Because there are situations where vector search isn't actually going to work that well, and where keyword search is going to work instead. So whatever it is you end up choosing, you want to ideally always be using a hybrid search approach in order to have optimal retrieval. And in Azure AI search, the optimal combination is hybrid search plus the re-ranker, which changes the rank of things in those results, right? So imagine it gets back 20 results from doing that hybrid search across vector and keywords, and then that re-ranker is going to be like, oh, okay, actually, let's pull these ones up. And that's really helpful because when we send these to the LLM, we're going to chop off and only use, the top 3 or top 5. So we really want to get that, those top ones to be the best ones. So that's why we recommend this combination here. So let's actually demonstrate that in code because that's always the best thing to do. All right, so once again, we're going to set up our connections to Azure Search and OpenAI. And now we're going to look at a situation here where vector search is not optimal. So this is, I'm searching for the exact string, $45. So I get the embedding, I do a search, and what do I see when it does the search? I'm going to see it. So all of the results it found do not have the text $45. So I was not able to find that exact text. Now, what you do see, though, is that it did return results. And this is something also interesting about vector search is that vector search, you'll pretty much always get results because there's always going to be some vector that is the closest, even if it's really far away. So that's another thing to keep in mind with vector search versus like a keyword search where you could actually get 0 results. With vector search, you're pretty much always going to get results because there's always something that's closest, even if it's super far. And now let's look at a text search for that. So this time we're just going to pass in the search query as text and not do any vector search and see what we get back. And we immediately see the exact string $45. So this is a situation where you can see that doing a text search, a full text search, works much better. Now, ideally, we'd be able to use both vector search and text search, and that's what we can do with AI search with hybrid search. So here we're going to pass in the search query and we're going to pass in the vector queries. And we're going to see how it does. So it did really well. So it managed to find, it combined these results. It figured out that this result from the text search was the best result and brought that rank to the top. And you can see in the score that it's much higher rated than the other ones. And yeah, so that's what's really nice about hybrid search and why we always recommend it, because it can take care of these situations like exact keyword search. Now, hybrid alone isn't always going to rank things high enough. So let's look at this example here. This is the one we showed before with learning about underwater activities. Okay, so we're gonna pass that in as a text query and as a vector query, and then we're gonna look at the results. And what we see is that the one with the underwater activities is actually number 3. So that's, probably would have been fine because we do usually retrieve 3 results for our RAG chat, but we really want it to be number 1 because this is the most relevant bit of content, right? We want this to be number 1. If our search is working really well, this should be number 1 for this query. So what we do is we use the semantic re-ranker. So that's a machine learning model. It's based off of Bing and how Bing does re-ranking. And you can enable it using query type equals semantic and then the semantic configuration name. So that'll use the re-ranker. And then what we see is that this time, those underwater activities are the number 1 result. So this shows you that, to really get optimal results, optimal ranking, you ideally want to use all these options. Now, these things do cost money. So the semantic ranker is an additional cost on top. So you can get like 1,000 queries per month for free in order to try it out and to see how well it's working. It doesn't work on the free tier at all. So you'd have to try it out on when not using a free account. But if you are able to try it out, it's really helpful to see if it's making a difference for the kind of queries that you're doing on your database. And here's some graphs here. This is from this amazing blog post. I recommend just reading the whole blog post because it's got so much good stuff in it. And I've also linked to this in one of the previous presentations because it really goes into so much interesting research where they try to figure out how to do optimal, data indexing and searching when making these, RAG applications. So here is where they did comparisons with keyword versus vector versus hybrid plus re-ranking. And then you see it just gets better and better as you keep adding these, abilities on. They also broke it down in terms of query types. And this is really interesting because this can help you think in terms of the kind of queries you're expecting to see in your data and you're expecting users to make for your use case. So, keyword queries, we already saw that, obviously like exact searches work best with keywords, but then vectors work better for other things. And you can look at length and stuff like that. So really interesting to think about the kinds of queries that you expect. Okay, that is my spiel, my demo. So I'm going to now go over to Sri, and I think Sri is going to share his screen so that he can talk about indexing data.
Thanks a lot, Pamela. And that was a much broader coverage regarding the AI search. So a couple of pointers regarding the semantic re-ranker. So it will play a key role on filtering out the results. As Pamela mentioned, during a vector search, even if there's an unmatched document, you will still get the results. And the semantic re-rank score ranges between 0 and 4. So if you have a high matching of the results with your search query, it will get you a better score. So you can use that criteria to filter the results and send a crisp results to the LLMs for a better experience. So talking about the data indexing, so we talked about the search, we talked about how to create an index, etc. So how to bring the data into the index. So that this is the segment is about. So there are a couple of options. And for regarding the vectors, there are again we have something called as BYOV, bring your own vectors, where you create the embeddings and then you put into the index, and then bring BYOE, bring your own embeddings. So you bring in the data and then we would embed and then we put into the index for you. So those are the couple of options we have in the AI search, and there are a couple of strategies how you can achieve it. So the first one is the manual indexing. So So I can show the RAG example for this. So this is the main about BYOE, bring your own vectors or bring your own embeddings. So you have a set of bunch of data. So this is all the PDFs you have, and then you want to index this PDF, and then you want to have an LLM experience on top of this PDFs. So what we can do is what we created for the RAG sample is something like a file strategy. So you have the blobs, you create the chunks from the blobs, and then you vectorize them, you embed them, and then you upload them to the index. So that's about the manual indexing strategy. uh, I can walk you through the code. So in this example we have a file strategy, and then we we kind of create an index. So we create an index with a definite schema, and this is a similar schema that Pamela shared in the previous sections. So right. So we create an index with the ID field, with the content field. That's the exact content from the PDF or the exact content from the chunks, and then we have the embeddings that we gonna create it, and then we have a category. This is for like additional properties, and then we have the source file where this gives absolute link to the file in the blob storage where we're gonna upload the documents.
Are you
Right.
showing code, by the way,
Oh
or
yeah, I'm
just
showing the
slide?
code. Is it shared?
It's
Oh.
only showing the PowerPoint right now. It sounds like
Uh,
you're talking over the code.
right. Let me see if I go
Yeah, you might have to like reshare the whole screen.
whole screen. Oh, okay. Let's just.
Sri is also on call right now, by the way. So we're hoping that he's able to make it through the presentation without getting paged too many times.
Sorry, guys. Let me.
Yeah, we'll get that code up.
All right. So yeah, this is the code from the rack sample I was talking about.
There we
Sorry
go.
about.
Yeah, and just zoom in. Maybe just zoom in a couple. Command plus. There we go. Beautiful. All right.
Yep. So this is about creating the index. So once we create the index, and then we're gonna run some samples. Like we're gonna run some uh, strategy, like how to chunk the document. So these are all PDF documents. So the best way is to get a chunks, like divide the documents into subset of paragraphs or sentences, and then you vectorize them. The couple of reasons behind is, as you know, the embedding models, they have a token limit of 8,000. I mean the OpenAI models, and also smaller the chunks, the better the search results, and the better the experience you get through the LLMs. So once you set up the index, and then now you run the now you run the section, like where you split the PDF, and then you get the chunks out of it. And once you have the chunks out of it, you create the embeddings. So we have all the helper functions in the rack sample. You can walk through. uh, and once you get the chunk, once you get the embeddings, you update the schema, and then you upload to the index. All right. So that's a quick overview of how can you bring your own embeddings into the index. But with the recent in the AI search, we have a feature called as integrated vectorization, where you don't need to worry about chunking. You don't need to worry about embedding the contents. You just give us the documents, and we will take care of it. So let me share an example for that. Let me again, switch back to my portal screen. Uh, let's show. All right. So I have an index, and I just created a search service, and then I didn't create anything. I didn't create any index. I didn't create any additional features. So I have this beautiful import and vectorized data. So this one we launched it in November. What does this like? It connects to your blob storage. So right now we support blob storage as one of the data source, but going forward, it could be a SQL, it could be a data lake, it could be anything. Since this is in a private preview, right, we support like a blob storage. So we choose a blob storage, and this has the same data as the sample data in the rack sample. Uh, where did it go? All right. Looks like I have a bunch of blob accounts, so I need to choose the right one. Let's see. Let me. All right, where did it go? All right, let me pick this one. And then I need to choose the content. So that's where all my PDFs are stored. And then I do next. So this one points out to the OpenAI service. So you need to have an OpenAI service created under your subscription. So choose your OpenAI service, and then you should have the embedding models, right? And then you just authenticate the API key, and then you need to acknowledge. And right now we are not focusing on text. So tomorrow there's a session from Matt where he covers all the image embeddings as well. And then we enable semantic ranker. So again, this is an option that we provide by default, but it's up to you. So this is only available on the basic and the standards queue. And then schedule indexing. So I need to talk a little about the indexers. So indexes are nothing but data crawlers that's available in the Azure AI search. So it can connect to your data. It can read it, retrieve it, and then index it, and then you can schedule it whether you want to run it once, or you want to run it hourly, or you want to run it 30 minutes or daily, or custom schedule it. I'll go over the next, and then it's just the object name prefix. So this will create bunch of objects which I'll walk through in a couple of minutes, and then I do click create.
So you said that this particular UI is in private preview?
I mean, it's available to customers, but this features
Okay.
in private preview, right? So since that's, I mean, we connect only to the blob storage. That's the private preview, but this is available to the users, end users.
Okay. Okay.
All right, cool. So it did something, and then it came to a search page. But before getting into the search page, let me show what it created, what that integrated vectorization feature created. All right, yeah. So all right, so this one, yeah, it created an index for us. It created an index for us, and then it created an index schema, and it automatically detected that we have a chunk. That's the text that would be extracted from the documents, and then we have the vector. That's the embeddings that it's gonna produce from the vectorization flow. And then these chunk ID and parent ID, it was created for the internal purpose, and then it was exposed. It's nothing to do with the search, but it's just for internal document management. Basically, if you have deleted a document from the blob storage, we need to track it, and then we need to delete all the chunks related to the document. So for that purpose, we created this chunk ID and the parent ID. And title is the title of the document. And then once we created the vector, we created the optimal algorithm. So we created the algorithm which we think would be the best. So that's the HNSW algorithm with all the search parameters and the cosine similarity. And also we created the semantic configuration as well. So we chose the title field, and then chose the chunk field as the content for the re-ranking purpose once you retrieve the documents. Apart from this index, we also created a skill sets. And what are these skill sets for? These skill sets are needed in order to chunk your documents and vectorize the documents. So we created it for you, and we introduced Azure OpenAI embedding skill. So this skill is responsible to produce the vectors for your chunks. And then there are a couple of items that are needed, like so you can create the skill on your own, or you can use the SDK or the samples that we have hosted in our public repos. I just I want to walk through a couple of important properties on the skill. So this skill needs a resource URI. This is nothing but the OpenAI resource URL, and then is the API key. So excuse me, this shouldn't be displayed. I need to talk with my backend team and ask them not to, send it through the API response. And this is a deployment ID. This again comes with the Azure OpenAI, uh, like the portal, like what deployment you want to have for the embedding. And inputs is a plain text, and then it's source is the document pages, and then the output is the and the vector. So this is something we called as output projection. So our index field is vector, but internally we produce something called as embedding. So that's the projection we map to. And for the text split skill, this skill is responsible to chunky documents, and so it has by default whatever we think would be the best, that has a based on our testing and benchmarking purpose, we have added that value into this feature. But again, you can fine tune it according to your needs. So the max page length and the max page overlap length and the pages to take, so it's 2500 based on internal benchmarking we had on our systems. And then these are the index projections, like if you have a different schema and how do you want to map it. So these are the basic fields that will be produced by the indexes, but if you want to map to a different field in your index schema, this will help too. So these are all the skills that we the in the vectorization feature created for you. So I talk. Let's do the search, and let's see if that indexes has worked. So it's in progress. So good. So it's processing. Right now we just have few couple of warnings. We don't have any errors. Again, this is all for development purpose, but if you want to move into production and once you set it up, it will work like a charm. All right, couple of warnings. Right, let me search for some documents and make sure the vectorizers they work. So on the search explorer, we have a query option. So we have the vector search by default, and then we hide the vector values. We just make it easy to read the results, and then we have the semantic ranker turned on. And let me ask some question. All right. Um. All right. Show my healthcare plans. So this is a hybrid search. So that's why I just type the questions into two sections. But you can use a pure vector search, or you could use a pure keyword search.
Well, you're going to compute the embedding for us. That's amazing.
Oh, that's true. Yeah, that's the main purpose. So the kind over here is text, meaning you just enter the text, and then the search service B will compute the embedding and will make the distance relation, and then we'll get you the results. This makes the work much easier compared to the previous one which I showed. So search, we might see some throttling because the indexing, yeah, it's still 429, so the still the indexer is in progress. Let's give it some time, but let me try again. All right, let's get some time, and then let me come back again. All right. So again, let me do this. Let me switch my screens, and then let's go to the further slides. All right. So I talked about the manual indexing, and there's a data ingestion guide, and then I talked about the integrated vectorization. It's in the next one. And for the cloud-based indexing, as I said, we have partnered with a couple of other data stores in the Azure. So it's a blob storage, Cosmos, Data Lake, SQL, SharePoint, and yeah, etc. And yeah, skill checks for indexes. So this is the major thing which I talked about, the new integrated vectorization feature. So there are a couple of skill sets that comes out of the box with the Azure OpenAI search. So one is the Azure Open AI embedding skill that produces the vectors connecting to the Azure OpenAI service, and there's a text split skill that basically chunks your documents, and web API scale. So if you don't want to use the Azure OpenAI, but if you want to use some other models that use self-host, you can always use the web API skill to do that, to achieve your own embeddings and put into the index. For integrated vectorization, and this is the whole flow which I talked about on the Azure portal side. Uh, right. So yeah. So right now we support only the blob storage, but going forward we have all the other data sources as well on the new flow. All right. On the rack sample, yeah. So we saw how to set up the integrated vectorization using the Azure portal. Okay, that's good. But in the rack sample, where we package everything into one single bundle, how can we do that? Again, let me switch screen to walk over the code. All right, let me zoom in. All right, so since this feature is in a preview, all the models related to the sample are in the preview SDK, and that's why we have like a workaround. And this pull request is in progress. It should be merged by this week. Yeah, once I'm done with the on call, we'll focus on the PR and then we'll get it done. Okay, what do we have in this strategy? So I showed like file strategy. That's like building your own vector and then building your own ingestion pipeline. You can do that, or you can use the integrated vectorization strategy where you set it up once and then it will vectorize and manage the documents on demand or as your needs. So on the integrated vectorization strategy, we use manage entity to a couple of pointers. So we use manage entity to connect to both blob storage as well as the OpenAI endpoint as a best practice. And you could see like some of the parameters, extra parameters have been added to the class. All right. So the first, or so let's talk up from the setup. How do we want to set up the vectorization strategy flow? So as earlier, you have an index schema. You would create an index, and once you create an index, the next thing is we need to set up the skills that would basically connect to your documents and then do the chunking and then vectorize them. All right. So we have created the index, and then this index schema is similar to what we saw in the previous sections with some little modifications like the one I showed in the parent ID, etc. And we have the indexer client. So indexes, they are the crawlers, or they are the whole unit which kind of connects to the data source and do the processing. So the objective is to we want to create an indexer, so we would create an indexer client, and then for the indexer client we want to show, hey, where are the documents. So we would like upload the documents to the blob, and then we pass it down as a data source connection, so that the indexes know like blob is my data source. And then once the data sources are connected, we will create the embedding skill set. So this embedding skill set, it creates the one which I explained, like the Azure OpenAI skill as well as the split skill. So I would start with the split skill. It's the same, like whatever we think would be the best for the PDF documents I have put in. Based on your needs, you can modify the parameters. So the split mode are pages. So like if like a 10 pages, like first extract all the pages from the PDF, and then within one page you get the maximum page length, like that is a 2 KB, that is a 2 KB of string. And then with a page overlap of 20, like between chunks have a string overlap of 20 characters. And then each index schema could be different. So this is the mapping we had I had for my index schema. But again, if your index has a different fields, yep, feel free to remap it. And once we have the split skill, the embedding skill, again, this is the skill that says, hey, produce embeddings for my chunks. So a couple of things. So This requires resource URI. This is nothing but the Azure OpenAI URI. So this works only with the Azure OpenAI right now. But going forward, as I said, if you want custom or self-hosted embedding model where you want to produce where you produce the vectors or embeddings, you can have it. And these are the inputs and outputs that the skill would produce. Again, the outputs is to map uh, with the fields in the index schema. So it produces an output of an embedding field, but then it maps to the vector field of the index schema. And then for index projections, so with each and every skill, we have a internal mapping. So like what corresponds to a page title, what corresponds to the page value, and then what corresponds to embedding, and how does it map to the index schema. So that's what index projections would take care. You can go without index projections, but if you have a definite schema or if you have a custom schema, I would strongly recommend to define the index projections. And once you create the skills, you just define the skills, you create the skill sets for the indexers, and that's it. So we have the data source ready, we have the skill sets ready. The next thing is we need to create the indexer, and then we need to execute it. So this is a section that would help us to upload the files to the blob. It's similar to the previous section, like on the manual embedding or the manual upload. And then you just create the indexer, and then you create the schedule for it. The advantage is that as long as the blob changes, so let's say you started with 10 documents and then you expand it to 100 documents, the indexer would look for the change in the blob state, and then it would pick up the new document. So you don't need to worry about how the index is getting updated, or how do you, if you want to produce a manual chunks of the index. So you can on demand, you can chat over your data with with indexes taking care of the documents that needs to be indexed. Or so that's about the integrated vectorization that we have the sample. Again, this is in the work is in progress, so it should be ready by end of this week. Yeah, switching over the screens, and all right. Yep. That's a that's about the vectorization for the rag chart repo. So manual indexing versus integrated vectorization. The pros is all the code is in local and is easy to change, and you can define however you want. But it's hard to connect to the indexes for the cloud. If you have multiple data sources, then you need to worry about how to have a best practice to connect, whether using the API key or the manage entity or the connection string, etc. And then you need to manually run the indexing job on yourself. With the integrated vectorization, you don't need to worry about what is the best strategy to produce the vectors, and what data source to connect, and when do you want to run. So everything, all the life, I would say the life management of the indexes, it's taken care of this feature. So the next is about the AI search advanced features. So let's talk about a couple of features which I would think would best help on the LLM chat scenario. The first thing is the analyzers. So by default, for every field on the index, the AI search, it comes with the English analyzer. But if your document is a non-English, any other language, you can choose analyzer equivalent to that language, and that will help in the better search experience to get the most relevant documents needed for your search. And then there's a custom analyzer. So if you have documents of specific patterns, for example, like an email ID or a numerical number, or some GUID or some unique ID within the document, it's better to put up a custom analyzer, so that it will help you to re-rank the document and then get a best result for the LLMs. And apart from analyzers, there are some scoring profiles. So scoring profiles are nothing but term boosting. In other words, so if you want a particular set of terms, especially in the keyword search, if you want to pop it up on the top of the result, use a scoring profile. So this is best executed with some experiments, with some benchmarkings, because not all scoring profiles would be suitable for a particular scenario. So I would say execute the scoring profiles with the benchmarking, and then it will definitely help the LLM scenarios. And apart from scoring profiles, as Pamela pointed out, we have the filter feature. If we have data across different document sources, and then if you want to have an isolation, you can leverage the filter. So the filters are executed before every search, so it will able to narrow down the scope you want to search for and get the better relevant results. Right. And for the next steps, yeah, I will turn back to Pamela, and then let me know if you guys have any questions.
All right, thank you so much, Sri. It's great to see things in the portal there. Actually, I'd never explored so much in the portal. So yeah, there's a lot to Azure AI search, and you can start with just making sure that you're trying to use as best of the retrieval mode with the hybrid mode, but then you can like really take it a lot farther as you discover which of your search results are working well and where you maybe want to make some improvements. So next steps are, if you haven't yet registered for the hackathon, do register for the hackathon at our little URL here, aka.ms/hacktogether/chat app. That's where you can register for the hackathon. That's where we've got a discussion forum where you can say hi, where you can ask any questions, and then get started on actually working on your hack. Most folks are working off of this repo here, our our rag chat repo, and it's right here, and we've got the document about how to deploy from a free account and from a student account. So you can go through this document. There's also a video going through that deployment, and that's what a lot of people are following. So that's what you can start your hack on, but then you can take it so many directions and bring in bring in your own data. And I've seen a lot of cool ideas in the forum. So start hacking, ask us any questions in the forum, or in the issue tracker for the repo, and we'll do our best to answer those questions, and to point you in the right direction for how you can keep going. Tomorrow we are going to have Matt, who's also from the AI search team. He's going to be talking about vision and image search, and should be showing us some cool demos that I know he's been working on this week. So that should be really cool, really exciting, and to see how we can bring images into RAG as well. So thank you everyone for joining, and thank you, Sri, for sharing your AI search expertise. And we look forward to seeing you at next sessions and in the forums. Bye, everyone.
Bye bye. Thank you.